Okay, so let's go. We are done with the on the dam system when the damping ratio is smaller than 1. I'm gonna skip too many mathematics because again you have to know ME430 or Y ratio before coming to this class. I'm just giving you hints of how the second order system and how high order system that today hopefully how they behave. Okay? But details of this you can find in ME430, the system dynamics. Because this class is mainly control, but just I'm giving you a glimpse of how they behave, okay, dynamically. So now today hopefully I can finish in the theory and simulating when the system is critical damp and the system is over damped, means that you have the excessive damping. For starting with this, we know that if you have a critically damped system, as you know, we have a pair of repeated what? Poles. I mean that if you plot it in the real and the imaginary for reminding you, okay? So hold on guys. So real and imaginary, as you know and I taught you previously, you have two repeated real poles on each other. So today only for both cases I'm gonna examine when the input to the system for any second order system is 1. F of s means that you are dealing with the input of the impulse. So having that, you know that x of over f, as you know the million times, is omega n squared in s squared plus 2 omega n, because for case of critical lamp, zeta is 1. Omega to zeta is 1 plus omega n squared. It's closed transfer function. Obviously, because you have two poles, repeated real poles, you can write as this S, say, plus P squared. S plus P, or P1 or P2, doesn't matter because it's the same, right? Yeah, that's it. That's right. I mean that you have to write like this. S plus, S minus, not plus. Minus P1 or whatever. P2 is squared. So we know that the F is 1. Okay, so you get X, the output of the system, gonna be omega n squared S minus P1 squared. Okay? So if you want to back to the time domain, you have to go over the Laplace inverse. And based on whatever I taught in the Laplace table, I hope that you remember it. Laplace of E minus AT f of t is f of s plus a. I taught you in the Laplace table. So exactly you have here, you know that Laplace of, guys, Laplace of ramp is how much? Now you know it is 1 over s squared. Oh, 1 over s squared. But this s is being changed to what? S plus a, s minus p1. That's right. So to remind you whatever I taught, here's minus is plus, is plus gonna be minus. So this is minus gonna be plus. So you see that the x of t gonna be omega n squared, okay, EP1t in t. Everyone understand what I have done? Here we go. Right? See what I'm saying, guys? So this is equals to omega n square E minus zeta omega nt in t. So you see, for the underdamped system, if you apply the impulse, this is the final answer. Being said, if I want to plot it, this is time, this is x. This is the input to the system for the critically damped system. Impulse. Now, remember, when we had the underdamped system, x of t was this. A e minus zeta omega nt sine omega dt. Right? Remember, guys? We had a harmonic associated with some decaying. That's why for underdamped system we had a harmonic vanishing. You have your notes. And this was when the zeta was smaller than 1. But here, do you see any harmonic? No. So that's why when your second order system is critically damped, you have this. There is no oscillation. So, and the zeta is 1. Understand that? Yes? So, by looking at the steady state phase, we don't need to utilize the final value theorem. You see that the steady state error signal is how much? 0 again. Because output follows the input when time goes to a large number. Now, I'm going to repeat this for this case when the system is overdamped, because these two examples enough that I extend whatever I'm developing here for the step, for parabolic, for ramp. Can I go to the next page? Huh? Yes? Okay. So when your system is overdamped now, you know that you have your notes that you have a pair of distinct real poles, minus zeta omega n plus minus omega d, zeta square minus 1. Remember that if you want to plot it on the real and the imaginary, these are the poles on the real axis. I taught you. So again, I'm saying I'm going to stick to the impulse input. F of s is 1. From here, you get x of s going to be omega n square in s minus p1 in s minus p2. Two distinct poles. And you know, this is a over classic that we have done 10 times in this class. P s minus p2. So this can be written as a s minus p2 plus b s minus p1 in s minus p1 s minus p2. Obviously, numerator equals to omega n square. So if you sort it based on order of s, you get a. I'm just doing very rapidly from my mind because I have taught this million times. A plus b is 0, and minus a p2 minus b p1 is omega n square. From here you get a is minus b, and if you implement here, you're going to be b p2 minus p1 is omega n square. So p is omega n square p2 minus p1. So p2 minus p1 from here gonna be minus zeta omega n, say plus. Guys, this is omega n. This is typo. Omega n zeta square minus 1 minus p1. Omega n square minus omega n zeta square minus 1. This with this goes to help. You get 2 omega n zeta square minus 1. So from here you get that the b gonna be, if I simplify this with that, it's gonna be omega n in 2 zeta square minus 1, and a is minus b, minus omega n 2 zeta square minus 1. And implement it here. So if you are done, I will move to the next page. Can I? Everybody? Being good. So being said, we get x of s gonna be omega n 2 zeta square minus 1. So because this is plus, I'm starting with this 1 over s minus p2 minus 1 over s minus p1. Going back to the time domain, again, we're going to have Laplace inverse. I know this is the exponential terms. So x of t for the overdamped system with the impulse input gonna be EP2t, means minus zeta omega n plus omega n zeta square minus 1 in t minus p1t e minus zeta omega n minus omega n zeta square minus 1 in t. Bingo. And this is the answer of the system. Likewise, of the critically damped system, do you see any harmonic term in the solution? No. So if I want to plot finally to make a conclusion for other cases, Tx, this is impulse input. This is, this is underdamped system. This is today we derive as what? You tell me. Critically damped system. This is overdamped system. The only difference with this is it's much slower. I'm going to show it in the simile than the critically damped system to settle down. Zeta greater than. So the only major difference between the overdamped that physically makes sense because you are applying excessive damping. You are applying excessive friction, if I want to talk physically, to the system. So it takes more time to settle down, and the mathematics confirms it. And if you look at the steady state phase of the overdamped system, again, ESS is 0. You don't need to implement the final value here. Clear, guys? Now I can make a general statement. How? I'm going to do that now by graphs, if you are done. So I want to make general statement. If the input to the system is impulse, I'm skipping the math of the rest of them because I'm teaching those in ME430 in detail, the topics of those course. So it is Tx. If your system is if your input to the system is impulse, as I plot it now, this is underdamped, this is critically damped, and this is overdamped. If you plot the response of, let me put the tags because you want to input some, as you know, zeta 1 and zeta greater than. Now, if I want to have the step input, I can generalize my conclusion. Tx and the step input. Here we go, unit step. Now you know, because I derived with you mathematically, this is gonna be underdamped with the overshoot. Remember that we derived many parameters for controller design. I'm skipping the legend because legend is here. So, and this is because in the critically damped system there is no oscillation like as the first order system acts. This is for critically damped, and from the overdamp I told you that it takes much longer time to settle down. Here we go. Overdamp system. When your f of s is a step. Now, if I want to go over ramp input, as I promised you in the beginning of this course, for any second order system or any higher order system, I'm going to hopefully teach this day or the next class that has a dominant poles acting as one of these cases. I'm going to teach you. So if you have ramp, okay, and so for underdamped, if you remember, we had the oscillation and then this constant error signal, remember? And for overdamp, zeta is 1, there's no oscillation, I'm gonna be like this. And let me change up the color of this because this is the input to the system. And for overdamped, it takes more time to settle. Here settles here, here settles here. Okay. And if I want to plot, okay, so f of s was ramp s square. Now, if I want to plot it versus parabolic as input, this is parabolic. For underdamped kind of oscillation on this, error signal increasing. For critically damped, no oscillation. No oscillation. Say. And overdamped, it takes more time to settle. Actually, there's no settle because error signal is increasing. So f of s is for the parabolic. Remember, ESS here was 0 for 3 cases, under, over, critically damped. Here was 0 for 3 cases. For 3 cases here, steady state error signal as we derived mathematically for the case of underdamped system was 2 zeta over omega n. And for here, for 3 cases is infinity. And we are done with the second order systems. Clear, guys? Yes? Good. Before going to Simulink and run this, I want to teach you more theoretical things here and then go to Simulink. These are for second order system, any second order system. But I'm going to teach in the ME430 that if you have such a circuit, Vn plus minus R1, C1, R2, C2, if I want to find the closed transfer function of Vc over Vn, I bet, okay, it's going to be a fourth order system. Or third order system, like S cubed plus S squared plus 2S plus 10. Bingo. Okay? Understand? Or if I add inductor here, it's going to be a fourth order system. Say L1, L2, for example. Going to be S4 plus S cubed plus S squared plus 10S plus 50. Oh, fourth order system. So how many poles this system has? I told you how many poles? Huh? P1, P2. How many is the order of this system? 4. Look at the equation in high school. Fourth order equation has 4 poles. 4 poles? 4 poles. P4. See what I'm saying? So let me plot this, guys. Just suppose, I'm giving you just imaginary numbers. I don't know the solution of this. We're gonna do it in MATLAB. Suppose this is 0.5. Oh my god. What is this? Are you walking? Turn off your camera, sir. Turn off your camera. Okay. Plus 2i minus 0.5 minus 2i minus 10 minus 15. I don't know. Just give me the numbers. What I'm going to do that because I'm going to teach you a concept here. If I plot the poles of the system, first of all, you see that all the poles on the right, on the left-hand side means the system is stable. So this circuit is stable, okay? Voltage of the capacitor over input voltage. So if I want to plot it, say is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, 10. So 1, 2, 3, 1, 2, 3. So you have a pair of complex conjugate poles here in point half here and point here. And the third pole is in 10 here. The other pole is very far, that's right. Here, the other, minus 15. Okay, that's fine. Guys, please stop if you understand what I'm doing. Now, guys, look at this. As we did previously, can I write this denominator like this? S minus P1, S minus P2, S minus P3, S minus P4, because we have 4 poles, that's right? Yes, everybody? Good. I'm asking because I wanted to make you understand this topic. So at the end of the day, we are just doing what? like we always did. Yes? To find the time solution. Good. Exactly. P4. Write it down because I'm continuing. Okay? Write it down. I want to continue about this. And you get some A's. I don't care. These are constants, right? You get some A's, A, B, C, D's. I don't care about those numbers. So this is, say, voltage of the capacitor that we want to calculate. And suppose that the input voltage is impulse. This is 1. I don't care what it is. It is impulse. This is an example. Everybody agree? Yes? Yes, everybody? Good. So, because this is the first step for designing controller, that's what I'm very emphasizing that you understand. Okay, so your VC was A over S minus P1 plus B S minus P2 plus C S minus P3 plus D S minus P4. I want to find the time series of voltage of the capacitor. Laplace inverse. Now any of you tell me what function gives you such, now you know it, this Laplace transform. We just did it a million times. Exponential, that's right. Yes? So you're gonna have VC of t gonna be A E P1t plus B E P2t plus C E P3t plus D E P4t. Bear with me, guys, okay? Okay, now I'm implementing the numbers. What was your P1? Minus 0.5 plus 2i. Minus 0.5 plus 2i t plus b. Minus 0.5 minus 2i t plus c. What was that? Minus 10. Minus, I'm writing very large, 10t, and you do, plus d minus 15t. Guys, I bet, because I taught you personally, you have seen this. A pair of complex conjugate poles means that you have which term? Means you have harmonic and decaying term, that's right? Yes? Look at when zeta was smaller than 1. Look at that. Okay? When your system is under that. So at the end of the day, as I taught you personally, you can write this as, I don't know, some E minus 0.5t means 2 zeta omega n. That's right. Say cosine omega d. This is your omega d 2t, remember? Plus some f sine 2t. Remember, this is the formula I taught you exactly when your system is underdamped. So this is underdamped response. But what I'm going to change is the color of this. You're going to tell me, Payman, are you stupid? No, I'm not. 0.5 plus CE minus 10t plus DE minus 15t. Good. Now I want that you please pay attention to me. This is high school. This is not even control of the engineering. Look at these two parts. What was the name of these two parts I told you in this class? Technically, decaying what? Decaying what? Term, that's right. Remember? decaying term, because decay with time. Decaying terms. Okay, guys, if I increase time from 0 to infinity, which of them vanishes fast? This term or these two? Vanish fast. Yeah, this and this, because this is almost 20 times of this. 10 is 20 times of 5.5, that's right? Yes? And this is almost 30 times of 0.5. So these two vanish very fast compared to this term. This is high school, not control. Yes or no? Huh? Everybody understand this? On the other hand, if I want to plot this, I'm going to plot with green. This is going to vanish like this. Forget about the harmonic. Only I'm talking about the E. It's going to vanish this like this. But these two that I'm plotting with the red and pink is going to vanish like this. And the other one this one gonna vanish faster like this, because there's a large number here. Everybody understand? Yes? So when your dynamical system working based on time and time begins, these two vanish. And they have no effect on the dynamics of the system. And that's why we name these two, compared with this, dominant poles. This is a technical name. Dominant poles of the system. These are dominant poles. On the other hand, I don't care how this behaves, because it's going to vanish. If I apply a step for this fourth order system, based on this, I know that your voltage is going to be like this, as I told you. See what? Yeah. No, we don't simplify the system. I'm just teaching you. If even, I'm going to give you an example. If maybe you have S10, you cannot say this is equals to S squared plus 2 zeta omega. No, don't. We are not allowed to do that. Okay? We are not allowed to do that. Okay? Your friend says whatever you taught like this, I can say this is almost S squared plus 2 zeta omega ns plus omega n squared. You mean this, that's right? Huh? Conceptually, yes. But physically, you cannot do that, because if you do that, you change the system originally. See what I'm saying? Huh? Okay. Yeah. Yeah, because you change the system. This is another system. Okay. So I'm talking about the dominant poles. So when the real parts of the poles, that's the rule. Please write it down from the next page. That's the kind of the rule. If real part of poles are almost 5 times of the other ones, we name dominant poles. I mean the others ones are the dominant poles. 5 times. Because they vanish very fast compared to the other ones. Okay, that's right. Here is 20 times. Here is 30 times. Another example that you may have, suppose that you have this x be a over s minus 1. We have real poles, s minus 7 S minus 10. So can you show me the dominant poles of the system? Because at the end, when you come to time, it's going to be A E T plus B. Let me do this plus. Okay. Yeah, sorry. Minus T, B E minus 70 plus C E minus 10T. Which of them vanishes fast? This or this? Yes, vanishes too fast. So the dominant poles of the system is this. It's dominant poles. I'm not saying you can ignore them. No, because you cannot change the system dynamics. So this is the dominant poles, affecting poles of the system. Understand? Now, even that your x, please a second. If your system is, I don't know, x over f is 10 over s 100 plus 500, I don't know what's between them. You have 100th order system. If you want to find it, find the poles of the system. It gives you which of them is the dominant poles. Yeah, you have a question? Yeah, no, actually, see, when you want to design a controller, okay, it's better that you know how the system behaves. Okay, so when you want to know how the system behaves, you have to know what's the dominant pole. Maybe a system has no dominant poles and they are very close. See what I'm saying? But if your system has a dominant poles, you know that, okay, this higher order system acts as a second order system, so I can design this controller with this gain. See what I'm saying? Okay? So, but maybe your system has no dominant poles. Who knows? If you don't have, so you have to go to standard routines for designing controller. But this is just a shortcut to examine the dynamics of the system, how it behaves. See what I'm saying?
So long story, like just a big picture. It's
Yeah.
just to know
What kind of yeah, you need D gain, I gain, PD gain, PI gain. You know what I mean? So if your system has a dominant pulse, okay. So when you have the system, for example, that suppose we have a command in MATLAB with the name of the solve. So you can say sim means symbolic. Sim x, if I remember correctly. Okay. Now your x is the symbolic variable in MATLAB. Okay. Suppose that you have this solve, and because like as even that to be consistent, I say sim s because we know our s variable. So solve. Let me look at this because I didn't know. S square S. So what you have to do, you have to just exactly type this here. S square S4 S cube to S square. Okay. You have to say, if I remember correctly, S power of 4 plus. Can you read for me? S cube. That's right. Plus 2S square. Right. Yes, guys. Plus 10S plus 50. Here we go. First, you have to design your variable of equation as sim. Okay. Then you solve this. Maybe I have to remove this. Yeah. Here we go. Okay. Roots. Are you kidding me? So maybe sim s. Yeah. So let me see. Yeah. Here we go. Okay. So what you're gonna do? You can do this. Let me click everything. So sim s. Then you can say this is the poles. Okay. After doing that, you can say double means convert to number. Poles. Here we go. So it says your system, despite what I derive, has two pair of complex conjugate poles. One of them is this, these two. Another is this, these two. See what I'm saying? So this is how you solve the equation in MATLAB. So okay, guys, these two real part in the left-hand side, but the other poles are in right-hand side. It's plus. Do you see that, everybody? Plus 1.5 means that your system is what? Unstable. So now by knowing the poles, you can judge the system dynamics. So if this is real and this is imaginary, it says a pair of complex conjugate pole here and another is here, for example. Whoops! As Michael Jackson said, dangerous. Your system is unstable. So now you have to design a controller to move these complex conjugate poles to here. Control means this. Everybody understand? So now suppose you have it like as a vibration course, if you had with me, if you had the system with the order of 10. So let me do it for like as S10 into just a number, okay? S9 plus 11, S8 plus 1, S to the power of 7, and plus, I don't know, 4, S6 plus 2, S5 plus 100, S4 plus 200, S3 plus 15, S square plus 400 in S plus 450. S10, S9, S8, S7, S6, S5, S4, S3, S square, S. Okay, if I do that, oh, and then double pole. Here we go. It's interesting. It says that your system has a real part because imaginary part is 0 and it's in the left hand side. A pair of complex conjugate poles in the right hand side, your system is unstable. I don't know even what the system is, but just look at it. Another real pole in the left hand side, another unstable complex conjugate poles, and the rest are the stable conjugate poles because they are in the negative. Real parts are negative. So only by looking at the poles, you can see this 10th order system that can be modeled as the vibration system of your upper body is unstable. Just give me an example, okay? I don't know what, because of these two numbers, 0.5, 0.5, 1, 1.6, 1.6, real parts. So I'm asking you, what's the dominant poles? We don't have any dominant poles here. We do not have at all. System is unstable. Okay? Understand everyone? Yes? Huh? Now, I remember that we applied all inputs to second order system. Impulse, step, ramp, parabolic. But still we have one input. What was that? What was that? Harmonic input or Bode plot. Remember? Now let me see your system for three cases. Your num is this. Your den is for underdamped system. I'm gonna be one underdamped system. I'm gonna be 0.5. Let me do this. 2 multiplied by 0.2 and omega n. I'm gonna be this 5 because it's omega n is squared. And here is omega n squared. Remember, in the coding for Bode plot, this is for, because I'm going to share with you, underdamped system. Omega n is 5. Okay, I'm going to do like that. Then den 2 for critically damped system. For critically damped system, the damping ratio is 1. I'm going to put again is 1, 5, and 25. For critically damped, den 3, 2 zeta for overdamped system is greater than 1. 2 zeta omega n and omega n squared. For overdamped system. Remember, when we plotted for the first order system, the Bode plot, we had the low pass filter, high pass filter. And in the first order system, we had no overshoot for, as we had for underdamped system of second order system. So keep this in mind. Now what I'm gonna do, first I'm gonna plot step, num, and then 1. Greet. I'm gonna save it as the Bode of second order. Okay. So if I run this, I said stuff like I'm getting older, guys. Bode, now and then 1. Okay. Oops. I'm just making big. I want to skip that half because I taught you. Just put SJ omega and do the analysis and plot it. Okay. Guys, for the first order system, for the low pass filter, we had this cut off the frequency goes down. This is underdamped system. We have overshoot. Do you see the overshoot here also? Yes, for underdamped system? Great. For, now let me do this. Then 1, then 2. No, let's do this. I'm gonna make system very underdamped. Means 0.01, then 2.05, okay, and then 3, okay, and 0.2. That's fine. All of them, they are under damp system, very under damp, a little under damp, under damp. So I'm gonna say, hold on, then 2, then 3. Okay. Look at here, guys. Exactly what I did for the plotting the step input. You're gonna see in when you for the body plot. What happened? Hold on. There we go. Okay. See, this is very. Why these are not going there? Oh. Oh my God. I'm stupid. Here we go. This is for very underdamped system. Exactly when we plotted the step input for the underdamped system, we had a higher overshoot. I increase the damping a little, again you have overshoot. Again you have overshoot. Exactly when your system is underdamped and your input is the harmonic, you're gonna feel this. When I was teaching the vibration course, if you had with me, we name it the resonance in vibration. If I want to scale in the vibration course, ME520, we name it the resonance. Okay, but here is not resonance. Okay, see what I'm saying? So for the underdamped system, you have such a peak here. Okay, with the harmonic input. Okay, now if I plot with 4 and 5, because we know that for critical and overdamped system we have no overshoot. I taught you today. That's right. So when you do that, as in the step or ramp or parabolic or impulse, there's no overshoot. See that for this purple line is for the critically damped, no overshoot or peak, okay, or in here no overshoot, okay, for overdamped system. Understood, everybody? Yes?
Yes, sir.
Now let me, for God's sake, I plot a third order system because I want to make a point. A third order system. Num2, then 6. 1, 1, 3, 10. First of all, let me solve this. Sims S. And what was that? Okay. I'm gonna make this SQ S 1, 3, 10. And what are the no, this is not good. Let me set it on. Yeah, good. So what are the coefficients? 1, 4, 3, 10. 1, 4, 3, 10. Now I want to plot body of a third order system. Third order system, guys. And compare with the underdamped system. Underdamped second order system. This is third. Yeah. What? Yeah, no, too, thank you. Okay, let's compare. Oh, I forgot to put. Hold on. There we go. First of all, the cutoff frequency of this, or peak frequency of this, is different, but third order system acts like as the second order system. See? Because it experiences peak. Why? Because the poles of the system you have a pair of complex conjugate poles and what? A real pole. Okay, guys, now you let me know. Do we have dominant pole here or not? A real pole, because this is at least 5 times of the real part of this. So this vanishes too fast. So on the other hand, you have what? A second order system dynamics. See what I'm saying? Are you following me? Yes? That's why it acts like as underdamped second order. This third order system acts like a is not. Second order underdamped system. See what I'm saying? Clearly with the cutoff frequency different from second order system. But I mean the profile. Okay? See? Peak. Okay? But the cutoff frequencies are different. Understand, everyone? So now, oh, we are over there. Okay, almost what I thought what I wanted to teach. So next class I'm gonna finish this. I'm gonna share this with you, but I have too many things to talk about this. Okay. So see you guys. Oh, okay. Yeah. Hold on. Don't leave.